Today we're going to show you some commercial heat pumps. We'll explain how a heat pump is a little bit different than an air conditioner, and we'll talk about the different types of heat pumps that you might see. Commercial buildings have lots of different types of HVAC equipment, so a heat pump can be applied in lots of different ways. So we'll kind of go through those and explain what that actually means for you. In order to understand how a heat pump works, we first have to understand how an air conditioning system works, because a heat pump is just an air conditioning system running backwards, or at least sort of backwards. So on the top left here, we're showing the cooling cycle. There's an outdoor unit and there's an indoor unit. We're gonna show you all kinds of different actual systems today, but they're always gonna have these components. There's a coil sitting outside and there's a coil sitting inside. The outside coil is the condenser coil and the inside coil is the evaporator coil, because that's what the refrigerant is doing inside the two pipes. The job of the evaporator coil inside the building is to absorb heat from your building. So there's a fan system running, it pulls air out of all the rooms, it brings it back to this coil absorbs the heat, and hence cold air comes back out the supply duct for you. It takes that heat and sends it to the outdoors, and it rejects it outside to the outdoor air. When you have a heat pump, what ends up happening is the condenser coil and the evaporator coil switch jobs. So you can think of it as if I picked up that outdoor unit and I brought it in and I set it in the middle of your office building, and I took the indoor unit and I set it outside. Those things are not smart enough to know that I relocated them, so therefore they would keep doing their current job, and one would absorb heat outside and the other one would reject heat inside. That's exactly what a heat pump is going to do, except I'm not going to physically move the two pieces. Instead, there's a reversing valve in there, and that reversing valve is going to flip, and instead hot gas will leave the compressor, and instead of going to the outdoor coil, the hot gas will go to the indoor coil. And the two coils just switch jobs. There's one extra moving part in a heat pump, and that's the reversing valve. So we got a few of the panels off of this unit so we can see the inside of a heat pump and the main component that is different, which is the reversing valve. This is what allows us to go ahead and switch from heating to cooling mode. So let's pretend we're in cooling mode right now. The refrigerant comes in from the indoor unit. It goes into this reversing valve, which is currently positioned in the cooling mode. So it comes out this next pipe. It makes its way through the accumulator and into the compressor. The compressor compresses the refrigerant to increase its pressure, so it's hotter than the coil outside. Comes out the top of the compressor and routes its way back into the other side of the reversing valve and out to the condenser coil where it can reject its heat. When we ask the system to go into heating mode, the reversing valve slides over and flips, and now the outdoor coil becomes the evaporator coil and the indoor coil becomes the condenser coil. So now the hot gas coming off of this top of the compressor comes into the reversing valve and it gets routed out back to the indoor unit, and it comes back in the other pipe from the indoor unit and goes to the condenser coil, which is now the evaporator coil when we're in heating mode, on the other side of the reversing valve, and then back down into the compressor to restart that cycle again. So essentially those two coils just switch jobs, and the compressor doesn't know what's going on. It just makes higher pressure and that's it. So this will be our first example of a heat pump. This is a packaged rooftop unit. We're starting with this one because a little over 50% of commercial buildings are heated and cooled with packaged rooftop units. So it's called the rooftop unit because normally it's mounted up on the roof. It could be mounted on the ground and ducted into the side of a building, but generally it's up on the roof. And it's packaged because everything is in this box. The heating, the cooling, the fan system, everything is in here. Nothing goes in the building other than ductwork and a thermostat. So a gas-fired rooftop unit or an electric rooftop unit can be upgraded to a heat pump version. It looks the same. It's the same cabinet, same fans, same coils, same everything. We're literally just adding a reversing valve to those. So that's gonna be the first way you can add heat pumps to your building, is replace your existing rooftop units. Now, if you have an all-electric rooftop, meaning there's electric resistance heat in there, switching to a heat pump rooftop makes a ton of sense in every scenario. A heat pump is always more efficient than regular electric resistance heat. So you should definitely do that. If you have a gas-fired unit, then you'll have to do the math and decide if you're doing this for economic reasons and based on what your electric and gas costs are, or if you're doing it for electrification reasons where you just want to start getting rid or reducing the amount of gas-fired equipment you have in your building. This is our first example of a rooftop. We'll explain how everything works in this when we explain the split systems in a second, because it works exactly the same. Everything's just in one box. In contrast to a package system like we just had on the rooftop, this is a split system where the major pieces are in two locations. This is the outdoor unit, and then there's an indoor unit. Now, if this was air conditioning only, this would be the condensing unit with the condenser coil, and the indoor piece would have the indoor evaporator coil, and they're connected by two pieces of refrigerant piping. However, this is a heat pump, so as you already know, this is both a condenser coil and an evaporator coil. This one happens to be a 3-ton size, which is used in residential and small commercial applications, but it is scalable, and it can go up to maybe like 130, 140 tons of capacity, which would be a much larger commercial building. This is another type of ductless system. This one is a mini split type system. So it's gonna be much smaller, typically 1 ton to maybe 4 or 5 tons capacity, so a lot smaller than the other ones we were talking about a minute ago. Obviously the big difference here is there's no ductwork. This is the outdoor unit. This is the indoor unit. Obviously today, and it's a lab setting, so you can see both at the same time. But this is both your evaporator and condenser coil. This is both an evaporator condensing coil, just depending on what mode we happen to be in. So this will get used in a lot of commercial buildings. Historically, we've put these into specialty areas, like maybe a server closet at a commercial building, just to run cooling only. But now more modernly that people are electrifying their building, we're using them in other areas as well. The most common example would be applications where you might have hydronic baseboard heat or radiators or steam heat or something like that. Then you'll add one of these heat pumps and you'll let the heat pump take care of all the cooling needs you have, because your building probably didn't have cooling before in those kinds of situations. It'll take care of all your cooling needs, then it'll also take care of your heating when it's more mild outside. Say, for example, I don't know, 10 degrees up to 60 degrees outside. And then when it gets really cold, then you'll go ahead and engage your boiler like you would have in the past. It's a good way to compromise and blend those two systems together. Now let's take that ductless concept to larger systems. This is a variable refrigerant flow system, or just nicknamed VRF. What this is an outdoor unit that happens to be piped to numerous indoor units. It could be 5, 10, 20, 30 of these indoor units. And it can send the cold refrigerant or warm refrigerant to them, just like all the other heat pumps that we talked about. This one, however, happens to be a 3-pipe system, which means that it can send both cold refrigerant to some zones and warm refrigerant to other zones at the exact same time. It ends up getting pretty crazy efficient in those cases, because you have a zone on the east side and a different one on the west side, and one wants heating while the other one wants cooling. It could actually take the heat from one zone into this machine and send it back out to the other zone instead of rejecting the heat out the coil. So you can use one zone's waste heat to heat up the other zone, and that allows you to get some pretty crazy efficiencies. But you'll see this on systems that are a little bit larger, frequently used on buildings that traditionally did not have cooling ductwork, and now you're adding cooling to them. And at the same time, you could do some of the heating work and then barely run your baseboard or radiator heat. But it's just another way to do a heat pump system in a building. There is one other type of ductless system that does come up in commercial applications. That is a PTAC unit, package terminal air conditioner. Technically, if it's a heat pump, it'd be PTHP, but that's not a good acronym, so we never say that. We call it a PTAC heat pump. This is the type of unit you see in pretty much every hotel in America. Those that slide through the wall under the window. Those are very easy to convert to heat pump versions, because every single PTAC slides to the same spot. It plugs right into the outlet. There's not really any effort to switch it from an AC to a PTAC. But that will be another system you could convert over pretty easy. Another thing that we can do with heat pumps is do a dual fuel system. That means we have 2 fuel sources. In this case, it'd be a gas-fired furnace with natural gas, or it could be propane or oil or something else, and a heat pump, both able to provide heat to the building. So it doesn't have to be a furnace. There are other ways you can do this with boilers and stuff that we'll talk about later, but a furnace would be a common scenario. This is typically more for smaller systems where you only have 3, 4, 5, 10 tons of cooling, stuff like that. But you can combine the two. So if you're doing a heat pump replacement because you want to take advantage of the low cost of running a heat pump in milder scenarios for outdoor temperature, this might be a good compromise. You run the heat pump when it's mild, 30, 40, 50 degrees outside. You run the gas-fired furnace when it's colder, negative 10, 10, 20 degrees, etc., and you get the best of both worlds. As your temperature drops outside, the heat pump becomes less efficient, whereas the furnace stays pretty much the same. So that as the heat pump gets less and less efficient, eventually becomes more costly to operate than the furnace, and then you can go ahead and run your furnace. If you're changing to heat pumps for electrification reasons to reduce your carbon footprint, then this obviously becomes a different discussion. But if you're just doing it to save energy and have good comfort, you can have a dual fuel system, and it works pretty well, especially if you have existing furnaces in place. You just swap the air conditioner for a heat pump and you're done. Our last example for you today is a heat pump chiller. Now, a chiller in general makes cold water, hence the name chiller. So it sends cold water out on the piping system. That cold water goes through all types of indoor coils where they can absorb heat from the building. and then it brings back slightly warmer water with all that heat from the building back into the chiller, where the chiller can do our regular refrigeration cycle, compress the gas and all of that, and reject the heat to the coils on this unit. When I have a heat pump chiller, what ends up happening is the reversing valve flips, just like it did in all the other heat pumps. And now, inside that refrigeration cycle, this coil out here is absorbing heat from the outdoors, and it's taking that heat and putting it into the water. So now coming out the supply pipe, I have hot water. Typically, not crazy hot, but like 110 to like 140 degrees, depending on the model of chiller, whereas a traditional boiler might be more like 180 degrees. So I can make hot water, but not crazy hot water. But it's enough to heat most buildings in most applications. So you could take a chiller like this and you could add it to your existing boiler plant and put many of the run hours on this, thereby running your gas or oil boiler less. Or you can completely replace your boilers with these. That's not as common, but you could certainly do that. The next step beyond this would be water-cooled chillers. And once we get to water-cooled heat pumps, water source heat pumps, it opens up a whole nother category of stuff we'd have to talk about, and that's for a future video. But I hope this gives you an idea of all the kinds of things you can do with air source heat pumps in your existing building, and you can make some upgrades to save energy and or help electrify your building for carbon reduction reasons.